Welcome to this explainer. Okay, today we're breaking down something that is absolutely crucial for the entire HVAC industry. We're looking at the UN Environment's quick guide on good servicing practices for flammable refrigerants. Look, if you've been in the field for a while, you know the landscape is shifting right under our feet. We're moving away from the chemicals we grew up with and stepping into this whole new era of ultra-low to medium global warming potential refrigerants. And hey, these new refrigerants, they're fantastic for the planet. But they bring a completely new set of challenges to the job site. So this explainer is going to equip you with the fundamental science and, really, the vital safety math you need to handle these new systems with total confidence. So here's our roadmap for today. We're going to cover the shift to green cooling, the flammability trade-off, navigating those danger zones, the AB123 of safety, and finally, we'll wrap up by calculating safe charge limits. Let's get right into it. Section 1. The shift to green cooling and protecting the environment. The source material lays it out perfectly right here. As this guide clearly outlines, our shift away from old ozone-depleting substances isn't just some passing trend. It is an absolute necessity for global environmental protection. I mean, for decades, the industry relied heavily on HCFCs like R22, right? They were non-flammable, super easy to work with, but the reality is they were punching a massive hole in the ozone layer and heavily contributing to global warming. So the global push for higher energy efficiency and climate protection means those old reliable chemicals, they're out. But as you can probably guess, this creates a really high-stakes trade-off. We get to save the planet with new refrigerants like R290, which is just propane, by the way, or HFC32. They have ultra-low to medium global warming potential. But the catch? We are now essentially dealing with highly flammable materials on the job. The days of just treating all refrigerants like inert, harmless gases are completely over. You really have to respect the chemistry now. Moving on to Section 2, the flammability trade-off and how we go about eliminating hazards. Okay, the whole foundation of fire safety relies on this, the fire triangle. For any physicochemical reaction to actually ignite a fire, you need 3 elements simultaneously present and in the right proportions. You need fuel, which in our case is now your refrigerant. You need oxygen, which is obviously in the air all around us, and you need heat or some ignition source to reach that auto-ignition temperature. So your core job as a technician is to systematically eliminate at least one of these 3 sides to prevent an explosion. And since you literally can't eliminate oxygen in a room and the refrigerant is the fuel, your main line of defense is aggressively managing ignition sources and keeping that fuel concentration as low as possible. That brings us to Section 3. Navigating danger zones, the science of combustion. Now, this right here is probably the single most critical definition to understand in the whole manual, the lower flammability limit, or LFL. Think of this kind of like a dangerous Goldilocks stone. If there's a tiny leak and the gas is too dispersed, the mixture is just too lean. It's not going to burn. But once the concentration of the refrigerant in that room hits this lower flammability limit, the conditions are just right for a fire if a spark gets introduced. Take a look at that red block labeled the unsafe range. You'll see it sits right between the lower flammability limit and the upper flammability limit. Interestingly, if the gas concentration goes above that UFL, the mixture is actually too rich to burn. There's simply not enough oxygen left in the air. But inside that red zone, man, that is where disasters happen. Your mission on every single installation is to ensure that even in the absolute worst-case scenario, like a total catastrophic leak, the concentration of refrigerant in the room never even gets close to entering that red unsafe range. Up next is Section 4, the AB123 of safety, decoding classifications. So how do we know what we're dealing with? The crucial point here is the ISO 817 classification system. It's great because it neatly maps out toxicity with the letters A or B, where A is lower toxicity and B is higher. Then it maps flammability with the numbers 1 through 3. 1 means no flame propagation. That's your old R22. But look at the bottom 2 rows. We now have Class 2L, which stands for lower flammability. R32 falls squarely in this A2L category. Then we have Class 3, higher flammability. R290, our propane, is an A3. This grid is literally your cheat code. It gives you an immediate, crystal-clear picture of the exact danger level of the cylinder you're holding in your hands. Let's head into Section 5. Calculating safe charge limits, the technician's formula. Okay, before we start crunching the numbers, we really need to define charge limitation. As the UN guide states, this isn't just about what physically fits inside the system to make it cool anymore. It's the strict, standard maximum amount of gas allowed, based on the room's specific size and exactly where the unit is placed. We calculate this for a very specific reason, so that if the entire charge were to leak out into a closed room, the concentration would safely stay below that dangerous lower flammability limit we just talked about.
To solve this, we're going to systematically step through the variables. Step 1, you identify the LFL of your specific gas. Step 2 is the height factor. And hey, here's kind of a surprising fact. Because these gases are heavier than air, mounting a unit on the ceiling is actually safer than putting it on the floor, which totally shifts the math. Step 3 is simply measuring the room's floor area. And finally, step 4 brings it all together in the ISO formula you see right here. It perfectly balances the chemical's flammability against the physical space of the room.
Let's actually look at a real-world scenario straight from the manual. Say you're installing an R32 wall-mounted unit in a 30-square-meter room. The LFL for R32 is 0.307. Because it's wall-mounted, our height factor is 1.8, and the area is 30. By plugging those specific known variables into our formula, we can find our exact safety threshold. Let's see what we get.
And there is our definitive answer. 5.63 kilograms. That is the absolute maximum allowable charge size for this specific installation. Even if the manufacturer says the condenser can hold more, you cannot, under any circumstances, exceed 5.63 kilograms in a 30-square-meter room with a wall-mounted setup. Now, the guide does also mention a secondary absolute maximum check, which is 39 times the LFL, or about 11.97 kilograms for R32. But since 5.63 is well below 11.97, our calculated limit is the one that stands. Guys, this math is your ultimate safety net.
As we wrap up this explainer, you now have the conceptual tools to handle the green revolution in cooling safely. We've seen exactly why we're making this massive shift, how to truly understand the fire triangle and flammability limits, and exactly how to calculate the safety limits for every single room you work in. So I'll leave you with this final provocative thought. The future of HVAC is undeniably green, but it's only as safe as the technicians installing it. So are you ready to master this math, respect the chemistry, and become a true leader in climate-friendly cooling? Thanks so much for joining me on this deep dive, and I'll catch you in the next explainer.